Hi, we're starting a new chapter on alcohols now, the homologous series. This series has a hydrocarbon chain, which we can call R, and on the end of a hydrocarbon chain, or in fact in any part of the hydrocarbon chain, there is a hydroxyl group, OH. That's what determines whether it's an alcohol or not. And here is what we're going to do in this first video lesson. We're going to have a look at naming alcohols, and then we are going to distinguish between primary, secondary and tertiary alcohols, so define what they are. Next we're going to have a look at physical properties of alcohols, i.e. their boiling points, so that's a study of the bonding between the molecules, and also have a look at the solubility of them. Okay. So just before we get on to the A-level stuff, let's just check your prior knowledge from GCSE, which is sort of general organic chemistry knowledge. Do you know that organic compounds are based on chains of carbon atoms, usually long chains of carbons connected to hydrogens? You'll remember that the carbon atoms have 4 outer electrons, carbons in group 4 after all, and they like to form 4 single bonds, or in fact a multiple of double bonds alternatively. So double covalent bonds, they're formed by sharing 4 electrons between a pair of atoms, like for example in carbon dioxide, where you've got 4 bonds. The carbon's got 4 bonds, but they're 2 double bonds. Okay, and lastly, the functional groups that are added to the chain of carbons affect the properties of a molecule. And as we said just now, the functional group that we're looking at here with the alcohols is this hydroxyl group. Okay, first of all, we're going to have a look at naming alcohols. So we're just going to do a whole bunch of examples so that you get the hang of it. Let's start off with ethanol. So ethanol. So you'll remember from before that M, E, P, B, etc. Is 1 carbon atom for meth, 2 carbons for eth, 3 carbons for prop, 4 carbons for bute, and then 5 would be pent, etc. So eth here is going to have 2 carbons in it, so let's draw our 2 carbons, and they're going to have hydrogens bonded to them like so. But in this case we've got an alcohol and the ending is ol, and what makes it an alcohol is to have an oxygen bonded to a hydrogen like that. Now why have I drawn it at an angle like that? Well, that's because the oxygen has 2 lone pairs of electrons that we can illustrate like that. Okay, so that's ethanol. We'll try another one. Let's draw 2-methyl propan-2-ol. So that would be written out 2-methyl propan-2-ol. Propan-2-ol. Okay, let's have a look at this name, because you might be asked to draw an alcohol and just given its name. So from ol, we know it's an alcohol, so we're going to have a hydroxyl group on the end of it. This number 2 tells us where in the chain that the alcohol group is hanging off. Propan is going to tell us that the longest carbon chain has here's 3 for prop. Alright, so our longest carbon chain is going to be 3 carbons long, and it also means that we've got a methyl group hanging off this main carbon chain, and it's going to be on carbon number 2. Okay, so that's what we can read from the name, and now what we can do is we can draw it. So let's draw our propan chain first, so 3 carbon atoms like that, linked together, single bonds, because otherwise it would be propen. So it's propan. So 2-ol. Let's draw the 2-ol. So let's call this right hand one our number 1 carbon. So the middle one would be number 2 carbon, and the left hand one would be our number 3 carbon. In which case, propan 2-ol is going to have our hydroxyl group. We don't have to draw the lone pairs in each time. So now we've got propan 2-ol. Now we've got 2-methyl as well. So as we said, the middle one is the number 2 carbon. So we've also, instead of a hydrogen, we've got a methyl group hanging off our number 2 carbon. So that leaves hydrogens coming off the other carbons. So we just fill them in like that. And we will have drawn 2-methyl propan 2-ol from the name. Okay, so what we can do now is start with the diagram and then name it. So let's start with this diagram. Let's start with 2 carbon chains. Let's have hydroxyl group off each end. And let's just have a bunch of hydrogens coming off the 2 carbons. Okay, so there's our alcohol. We know it's an alcohol because we've got hydroxyl group. In this case, we've got 2 hydroxyl groups. So the first thing we're going to do is we're going to count the number of carbons in the chain, and we count 1, 2, and so that is going to be eth, right? So, and it's no double bonds because it's going to be ethan. Now we have 2 hydroxyl groups, so it's going to be a diol. Okay, but we need to tell the reader what carbons the hydroxyl groups are hanging off. So we're going to say, let's call this carbon 1 and this carbon 2. So the first hydroxyl group is coming off the first carbons, and the second hydroxyl group is coming off the second carbon. So it's going to be ethan 1, 2, diol, like that. Sorry, slight correction there. Let me just say that when we've got 2 hydroxyl groups, we keep the E on the alkane name. So this would be ethane 1,2-diol. Whereas we don't do that when there's only 1 hydroxyl group. So now they're all named correctly. Let's do one more. Let's do cyclohexanol. So let's write that out. Cyclohexanol, we know it's an alcohol because of the ending OL. In this case, it's a cyclical molecule, and we know that we've got 6 carbon atoms joined together. So we can draw a hexagon of carbon atoms. Like that. And in this case, we don't need a number because the hydroxyl group can come off any of the carbons. It's all the same. But if we had other groups, then this would be carbon 1. Forgive me for not writing out all the hydrogens and the carbons. Let's leave the structure like this just to save a little time. So there you have it. There's cyclohexanol. So let's move on to have a look at the different types of alcohols in terms of whether they're primary, secondary or tertiary. So the shorthand way of writing this, primary, you might sometimes see written as 1 degrees and 2 degrees and 3 degrees for primary, secondary and tertiary. What we mean by a primary alcohol is one where you've got your alpha carbon, or your carbon number 1. Your alpha carbon is the carbon that the functional group is attached to, in this case the hydroxyl functional group. So we've got an alpha carbon, and in a primary alcohol we've got 2 hydrogens and 1 alkyl group coming off it. And that's a primary alcohol with 2 hydrogens and only 1 alkyl group coming off that alpha carbon. Whereas in a secondary alcohol, there's your alpha carbon, and here's your hydroxyl functional group, and in this case we're going to have 2 alkyl groups. We can call them R1 and R2, and the last of the 4 bonds from that alpha carbon is attached to a hydrogen. So that's secondary, and secondary implies 2, doesn't it? And we've got 2 alpha groups, and primary implies 1, doesn't it? And we've got one alkyl group there. So I think you can guess what a tertiary alcohol is going to look like. As our alpha carbon, there's our hydroxyl functional group, and then attached to the alpha carbon, it's going to be 3 alkyl groups. They might be methyl groups, it might be propyl groups, they could be anything, they could be different, but they're alpha alkyl groups, and they're all attached to that alpha carbon, which means that alpha carbon doesn't have any hydrogen attached to it, which of course does affect the properties of these alcohols. So let's draw propan-2-ol. Let's draw propan-2-ol. Right, it's going to go to blue. You'll see why in a minute. So we're going to draw propan-2-ol. Okay, so prop means we've got 3 carbons, like this. Propan-2 means the hydroxyl is going to come off the second carbon, and the rest of it just got hydrogens. Quickly draw those in. And so what you can see is, changing colour, that this is a methyl group. Right, so we could call that R1 if we wanted. This is a methyl group. It happens to be the same as R1, but it doesn't have to be. In this case it is. Let's call it R2 anyway. And here we've got a lone hydrogen. So you can see that propan-2-ol is going to be a secondary alcohol. And if instead of this hydrogen here we had, let's say, you could have another methyl group, CH3, in which case that would be a tertiary alcohol. Okay, so now we're going to move on and have a look at the physical properties of alcohols. And the physical properties that we're particularly interested in are the boiling points and solubility. Okay, so first of all, let's have a look at boiling points. And here what I've got is a little table of boiling points of alcohols here. And what we can do is we can compare those boiling points to the relevant alkane. So you can see that methane can be compared to methanol. So we've got 1 carbon, but in the alkane, the boiling point is much, much lower. It's minus 164 Celsius, whereas the methanol is 65, much higher. So given that room temperature is about 20-25, then methanol is going to be a liquid at room temperature, whereas methane, of course, is a gas at room temperature. So why the difference? They've both got 1 carbon, and then we can summarize the difference by considering the hydrogen bonding that exists. So let's draw methanol. Okay, so meth has got 1 carbon. We're going to have an oxygen and a hydrogen. Let's draw in oxygen's lone pairs, and just to be complete, we'll add the 3 other hydrogens here. So that's a little displayed structure of methanol, and we can draw another methanol molecule. We will in a minute, but let's just consider the electronegativities of these atoms in this molecule. So as we know, oxygen is very electronegative, and it's got a lot of charge density associated with those lone pairs. So it's going to draw electron charge towards itself. So it's more probable that electrons be found nearer the oxygen than either the carbon or the hydrogen, but especially the hydrogen, because hydrogen is the least electronegative of those 3. Okay, so what you're going to notice is that we're going to get a delta negative on the oxygen, and that's going to leave a delta positive on the hydrogen. And so what we could do then is draw another molecule of methanol, like so. And in the same way, the partial charges will be arranged the same way. So this hydrogen is going to be delta positive, and that oxygen is going to be delta negative. And so there's going to be a force of attraction between the negative area and the positive area, particularly the lone pairs. And that force of attraction is known as a hydrogen bond. And as you know, those hydrogen bonds are they're the strongest type of intermolecular force, stronger than dipole-dipole, stronger than van der Waals or London dispersion forces, and that's why we've got a much higher boiling point for the alcohol compared to the corresponding alkane. Because in the alkanes they're not polar, there's no hydrogen bonding, and therefore less energy is required to separate those alkane molecules than is required to separate the alcohol molecules. Okay, so that's hydrogen bonding in alcohols, explaining the boiling points. But there's one other interesting point about boiling points of alcohols. So let's have a look at this other chart here. And now we're just looking at boiling points. And what might be interested is to have a look at tert-butanol here and compare it to butanol. Okay, so same number of carbons. So we've got 4 carbons in butanol, but butanol is just a straight alkyne chain attached to a hydroxyl group. But tert-butanol is going to look like this. Okay, so we've got our alpha carbon attached to our hydroxyl group, and then we've got three CH3 groups hanging off the carbon there. And as you can see, the boiling point of tert-butanol, about 82, compared to normal butanol, much higher. That implies that the bonding, the intermolecular forces between butanol molecules is stronger than tert-butanol, which let's say weaker. Okay, so let's just explain that. Well, what we can see is that there's going to be more steric hindrance. I'll write that down, that might be a new term for you, steric hindrance. With tert-butanol, it just means that these molecules can't get as close to each other as when they are flat or linear. All right, so let's draw butanol out, 1, 2, 3, 4, with a hydroxyl group. You can see that they're going to get closer to each other than the bulky tert-butanol. So the hydrogen bonds are going to, there's not going to be as many hydrogen bonds, and the van der Waals forces are going to be weaker as well, because the chains can't get as close to each other. So that explains boiling points. Let's have a look at solubility. Let's move on to a new slide to have a look at solubility. So let's just write solubility up here. Okay, so to explain solubility, let's draw a molecule of ethanol. I want to draw those hydrogens in just to save a little bit of time. And if it's going to be soluble in water, solubility, let's put water in brackets here. If it's going to be soluble in water, then it's going to have to make some sort of bond or attraction to a water molecule. All right, so water, of course, is polar, just like ethanol is. And so let's draw a water molecule like this. And it's going to be polar. Let's draw our polarities in. So water, oxygen is going to be delta negative. Hydrogen and water is going to be delta positive. This is going to be delta negative, and this is going to be delta positive. So just like we drew between the to ethanol molecules. On the previous slide, the water molecule is going to interact via hydrogen bonds with the ethanol molecule in the same way, and that means that they are infinitely soluble. Infinitely soluble just doesn't mean that it just means that there's no limit to how much ethanol you can add to the water. It will dissolve. So let's have a look at this table. You can see that the small molecules are infinitely soluble. So here, the smaller alcohols are infinitely soluble, but then gradually, as you get longer chains, until you get to decanol, it's actually not soluble in water. So let's explain that while we're at it. So let's draw a long alcohol. Right? To save me drawing all the carbons and hydrogens, let me just do the structure like that. Right, and then we've got a hydroxyl group at the end there. So this is going to be, let's change it up a bit of colour. This is going to be our delta minus, that's going to be our delta positive. And so we can describe this part of the molecule as our hydrophilic part. But this part of the molecule is hydrophobic. It's just a carbon-hydrogen chain. Hydrophobic. All right. So as when it gets to 10 carbons long, the hydrophobic nature of the chain hanging off the hydroxyl group dominates, and so it makes it insoluble in the polar water molecules. So there we have it. That's just about it for the introduction. Let's just go back over our learning objectives, make sure we've covered them all. We've had a good go at naming them, 3 or 4 different alcohols we named. We had a look at primary, secondary and tertiary alcohols. So 1 R group, 2 R groups and 3 R groups hanging off the alpha carbon. And then we had a look at physical properties, that was boiling points and solubility. So there we have it. That's our introduction to alcohols. I hope that's been clear.